Intro to Stats. We're going to start Chapter 5 today. We're going to be looking at normal probability distributions in Chapter 5. All right, our goal in this chapter is just to cover the first 3 lessons, and that should take us up to the end of the semester. Okay, we're going to start with normal distributions. We're going to interpret graphs of these and find areas under the standard normal curve. Okay, so back in Chapter 4, we focused on discrete probability distributions. And those included binomial distributions, Poisson, and geometric discrete probability distributions. A discrete variable, these are things, again, that you can count, things that you can't have part of something. So discrete, remember, were things that you can't measure, so they were countable things. In this chapter, we focus on the continuous random variable. And so with those, we have an infinite number of possible values. So these are things that can be measured, like time, weight, things like that. So this first statement says hours spent studying in a day would be considered continuous. It's a measurement of time. And we'll go on from here. All right. From there, we're going to look at your normal distribution. Now, you guys already know about the bell-shaped curve. You've had it before. You know that this measures the probability for a random variable x. We put the mean here in the middle, and so on. And we call this guy the normal curve. All right, we've had this slide already before too. We know that the total area under the curve is 1. We know our curve is bell-shaped and symmetric. We know the total area under the curve is 1. I think I already said that. I should back up. Number 1, the mean, median, and mode are equal. And then back to number 4, this curve approaches the x-axis on both sides, but it never crosses below, and so forth. All right, we also know that if we go out from the mean, we're going to go out 1 or 2 or 3 standard deviations on both sides. Now, what we haven't really talked about before would be this thing we call a point of inflection. So a point of inflection is where your curve changes from concave up, we'll call that concave up, to concave down. So concave up is a way to say like the curve would hold water, and concave down, the curve would not hold water. So it's upside down. Where it switches, where the curve switches from concave up to concave down, we call that an inflection point. We study inflection points a lot in calculus. All right, oh, and I should say where you have inflection points, that's going to tell you where one standard deviation is on each side. Okay, so what we can gather from this slide is that when we have the same mean, so we have the same mean on each graph, or at least for the first 2. When we have a bigger standard deviation, we see that the curve is more spread out. And when we have a larger standard deviation, I'm sorry, I'm saying it backwards. When we have the larger standard deviation, the curve is more spread out. When our standard deviation gets a little bit smaller, our curve is more compact. Over here, the difference between these 2 graphs would be that the mean has changed, but the standard deviation is the same. So the graph has the same shape, it's just slid down to the left. Okay, so now which curve would have the greater mean? So if I'm looking at these, I know that if I find the halfway point on B, so I know the mean for B is 12, and I know the mean, the halfway mark, for A is 15. So which curve has the greater mean? A does. Now, standard deviation. We talked about when a curve is more spread out, it's going to have a greater standard deviation than a curve that is compact. So B has the larger standard deviation. Okay, so this example, the heights of fully grown white oak trees are normally distributed. The curve represents the distribution. What is the mean? Excuse me. And what is the standard deviation? So if we find our halfway mark, we have our mean. Okay, and if we try to kind of estimate where our point of inflection is, so where does it start changing concavity? Probably about right in here, I would imagine. So I'm going to come out over here the same amount. I'm going to drop down. And what is that? So that's probably about 91, 92, 94. So the difference between these two is your standard deviation. Let's get the right notation. Okay. So our mean age would be, our mean height would be 90 inches, 90 feet probably, 90 feet with a standard deviation of 4 feet. Yeah, there it is, it's in feet. So we can add feet onto these. Okay. Now, here's some things you need to remember. This is a normal curve. So when I say 0, 1, 2, 3, I am now looking at the z-score curve. So the 1 would represent 1 standard deviation out, and the 2 represents 2 standard deviations out, and so forth. 0 is the mean when we have everything standardized by our z-score. Let's see, okay. So you need to keep this equation in the back of your mind. We're going to be using it a lot in future lessons. And you've already had it before. So it's just how you find a z-score. What we're going to do in this lesson and coming up lessons, we're going to take your normal curve, where your mean can be anything, and you're going to switch it over to a standard normal curve. And we do that with z-scores. And when you flip all of your probabilities from here to those with z-scores over here, that gives you a curve with a mean now of 0 and a standard deviation of 1. From here, we can use a table to find the cumulative area under the curve. Now remember, the area under the curve, all of this area is going to be an area of 1. So you're going to be given a particular z-score and you're going to be asked to find its area. Now, there is a table for this, and the table is in the back of your textbook, so you might want to go ahead and get your book out. It's table number 4. It's on pages A16 to A17. Okay. So what they're telling you in this slide is that you're going to read these areas basically from coming from the left to the right. So basically we start over here with a z-score of negative 3.49. That's roughly the z-score on the very left, and that area is going to be 0. As I move this way, the area is going to get bigger. And so the cumulative area increases as we go across. If you make it from here to the halfway point, then your area is 0.5. So the area of this side is 0.5. That's what they're telling you in number 3. Okay. Again, if I keep moving all the way across, I'm going to be at an area of 1. So halfway is 0.5. Okay. So the first thing we're going to do here is I'm going to just show you how to use the table to find the area. Now what I'm going to do for each of these is also sketch a random, a standard normal curve. So I would encourage you to graph these out as well so that you get used to them. All right, we know here in the middle we have 0. I'm finding a z-score of 1.15, so if I put 1 here, 2 here, and so on, 1.15 is roughly here. You're interested in finding the area, all this yellow. So the area of the yellow is going to be found by looking on your table. So you're going to go to 1.1 first, and then you're going to find the 0.5 second. So 0.05. So where these two intersect, that's your area. Okay, if I wanted to go with a z-score of negative 0.24, here's 0, here's negative 1, negative 2. Negative 0.24 is pretty close to 0, so it's like right here. And I want to find the area that corresponds to that z-score. So I want to find this area right here. Okay, so on my table, I'm going to go to negative 0.2. Then I'm going to look up the 400ths. And then where those two intersect, that's my area. Okay. So we've just reviewed how to use a table to find the area. And basically, if we're going on the left side of a z-score, that area is our answer. That's what number or this slide is showing you. However, if we want to go on the right side, we're going to have to take our area from the left and subtract it from 1. So this z-score here is 1.23. I'm looking for the blue area. I know that the entire area under the curve is 1. So what I'm going to be doing is I'm going to take the area on the left side from my table and then subtract it from 1 to get my final area of 0.1093. If I'm in between, let's say I want to find the area here in blue that's in between two z-scores, I'm going to find basically the area, you're going to find the area for both z-scores. So the one here on the left of negative 0.75 is 0.2266. The area left of 1.23, so that's all of this, is 0.8907. So we look both of those up in the table. And then if we take and subtract the length basically of the purple against the pink, and you subtract those two areas, you'll have blue, which is what's in between. Okay, so then I have some examples here that follow. Now I'm going to pause this video here so that I don't run over my 15 minutes, and then I'll pick up again in the second video.